Hi friend, good morning to all. I am here again for the course Aircraft Stability and Control. Today is my 37th lecture. In this, I am going to discuss about longitudinal modes which are related to the aircraft dynamic stability. In this lecture, I am going to cover these topics: longitudinal linearized equation of motion in Laplace form, characteristic equations, 3 degree of freedom analysis of longitudinal modes of motion, characteristic equation of short period mode, characteristic equation of long period Fugit mode. In this lecture, we are going to answer the following questions. What are the short and long period oscillation, effect of natural frequency and damping ratio in the dynamic stability? These topics I am going to cover. In the previous lecture, I have discussed about the equations of motion in the longitudinal axis. That is the 3 equations. One is in motion in x direction, the force which is acting in x direction, the force which is acting in z direction means vertical direction, and the moment which is acting with respect to the lateral axis means only pitching motion in which nose is going up or down. These 3 equations of motions we are discussing till now. However, in our derivation part, we have derived all the 6 equations of motion. In this, we were having the 3 force equation. One is Fx, which is force in x direction. Another is Fy, the force in the y direction, or this is called the side force. And the force which is acting in the vertical plane, that is, you can say, the gravitational force or the lift force which are acting perpendicular. And also we have discussed about 3 moments, that is the pitching moment, rolling moment and the yawing moment. But in the longitudinal, when we discuss about the longitudinal motion, there are only 3 equations of motion, and here the perturbed equation of motions are mentioned here. We will now use the power of Laplace transform to recast the aircraft equation of motion developed earlier. The longitudinal linearized differential equation of motion for the aircrafts is u dot is equal to minus g theta cos theta 1 plus x sub u plus x tu u plus x alpha into alpha plus x delta e into delta e. This is the force in perturbed force equation in x direction. The second equation is the perturbed force in z direction, where w dot minus u1 q is equal to minus g theta sin theta 1 plus z u dot u plus z alpha into alpha plus z alpha dot into alpha dot plus z q into q plus z delta e into delta e. Third one is the moment equation, which is q dot, it is pitching moment, rate of pitching moment, that is q dot is equal to mu, where mu is the moment in x direction, mtu, it is moment in x direction due to the thrust force, m alpha into alpha, it is moment due to the variation in angle of attack. Here, a variation of moment due to the thrust and angle of attack. Here, variation of moment, that is m alpha dot into alpha dot, mqq plus m delta e and delta e, where delta e is a deflection of elevator. So these equations have 5 variables. These are u, theta, alpha, w and q, and here delta e is a forcing function. Here we have one forcing function. Being 3 equations and 5 unknown, solving is quite difficult. So from the kinematic equations and the assumptions of initial trimmed flight with the wing level, we can solve these equations. So if we take these assumptions, we get here that Q is equal to theta dot and Q dot is equal to theta double dot. Okay, so this theta dot is a pitching angle. So this is the rate. So also for a small perturbation, we can assume that alpha is equal to W by U1 and so this W is equal to alpha into U1 and W dot is equal to alpha dot into U1. Therefore, our aircraft motion variables are reduced now to only three. They are alpha, U and Y. These should be thought of as the output for our systems of differential equations. So now with zero initial condition, the Laplace transform of the above equations, we can write that S because we are transforming to the Laplace to solve these equations to the simple algebraic equations. So it is equal to minus g theta into s cos theta 1 plus x us plus x t us. Wherever alpha, these all variables, we have added s here and everywhere. So in the same way, we have made in all the equations of previous one. So combining these terms, this yields to the s minus xu minus xtu us we have taken separately minus x alpha into alpha s plus g cos theta 1 theta s is equal to x delta e into delta es. Like this, here we have all the us item in the one, then alpha s in the another column, and all we have made in the same fashion. This we can see that here that in the matrix form we can write that s minus xu minus xtu, and the second column is this and third column is this. Here we have made us alpha s and theta s. This is equal to here x delta e, z delta e and m delta e into delta es. In the terms of the transfer function here, us by delta es, alpha s by delta es and theta s by delta es. Okay, so here we have here again in this we can write here this us divided by delta es, alpha s divided by delta es and theta s divided by delta es, and here it is the same matrix which was the earlier we have made it. So each of these three longitudinal transfer functions can be determined using the Cramer's rule. It is important at this point that each of these transfer functions can be represented as the ratio of two polynomial in the Laplace variables. So here we can write this thing as us by delta es is equal to au s to the power 3 plus bu s to the power 2 plus cus plus du divided by e s to power 4 plus f s to power 3 plus g s square plus hs plus I. Like this we have made for us by delta e, alpha s by delta es, theta s by delta es. Okay. So here all the three longitudinal transfer functions have the same input. In all these equations we have delta e as a input. This delta e is your elevator deflection and the same denominator. Okay, in all the three equation denominator is same. There is a separate transfer function for each of our three longitudinal motion variable, that is u, a and y. Also, each of these transfer function has the same characteristic equations. Each are having the same characteristic equations, and these equations are e s to the power 4 plus f s cube plus g s square plus h s plus I is equal to 0. the characteristic equation determines the dynamic stability characteristics of the response, and therefore all three transfer functions will have the same dynamic characteristics. Parameters such as zeta, omega n, and tau. So this zeta is your damping ratio, omega n is here is the natural frequency, and tau is a time period. So here the next is 3 degree of freedom analysis of longitudinal modes of motion. So now we will see that how these equations are useful for determining that aircraft is in the dynamic stable or not. So here we have 3 motion variable in the longitudinal equation of motions. These are u, alpha, and theta. So it's called 3 degree of freedom. The fourth order characteristic equation for longitudinal motion can be written as the product of 2 order oscillatory polynomials. As mentioned here in this equation, this you can see that here we have got 2 polynomial. So here first one is s square plus 2 zeta sp omega n sp s plus omega square n sp, and another equation is s square plus 2 zeta ph omega n ph s plus omega square n ph. So here ph stand for the Fugit and sp stand for the short period. So sp refers to the short period mode and the ph refers for the Fugit mode. All airplanes have these 2 longitudinal dynamic modes. Every aircraft will have these 2 dynamic modes. These 2 dynamic modes are the short period mode, another is called the long period mode, another name is Fugit. So here these 2 equations will tell that aircraft is in the short period or in the long period modes. These polynomials can be thought of as the separate characteristic equation that defines the dynamic characteristics of its respective dynamic mode. The coefficients and roots of each characteristic equations change with flight conditions. So airplane mass, mass distribution, airplane geometry, and aerodynamic characteristics. So these coefficients will change as per the aircraft mass, mass distribution, how the mass, the fuel tank, the bombs, the passengers, the equipments, how they are placed inside the aircraft. As per that, all the coefficients will vary, and we can find out that aircraft is stable or not. These changes translates to changes on X or Z, but fundamental presence of the short period and the Fugit mode is maintained. So here we can see that characteristics of short period mode. So just before I have discussed that we will get the 2 types of mode in the longitudinal motion. One is the short period, another is a long period. The long period mode is also called the Fugit mode. So first I am going to discuss about the characteristics of the short period mode. So in this we can see here that the short period mode is characterized by complex conjugate roots with a moderate to relatively high damping ratio. So in this moderate to relatively high damping ratio, zeta will be there, and the relatively high natural frequency and the damped frequency. So this frequencies also will be very high, and this will be the damping ratio will be moderate. It achieved by trimming the aircraft and then distributing it from trim with a forward, aft, neutral, forward and aft natural pitch input called the doublet. The resultant response back to trim may be either first order exponential decay or the second order oscillatory decay. Okay, so if it is the first order, it will be decaying. This you can see here that here 3 variables are there, u, alpha, and the theta. Here you can see the trim condition. Aircraft is flying in this condition. Due to some disturbance in the u, it is going like this, and immediately it is coming here up to this point is 5 seconds, but less than 5 seconds it is coming to the equilibrium position. Same way, if we are disturbing the angle of attack, it is disturbed. You can see here, if the velocity is high, the angle of attack, it is a positive, so here it is a negative. So this, if u is increasing, alpha will decrease. If alpha is increasing, u will this decrease. It is a inversely proportional. That I will explain this thing in the next slides. And here is the pitching. So this pitching will take a lot of time in this. Okay, so pitching, it is reducing but taking some more time. Now, the next is a characteristic equation for the phugoid mode. So in this phugoid mode, the phugoid mode is characterized by complex conjugate root with a relatively low damping ratio and naturally damped frequency. Means in this very low frequency is there comparing to the short period mode, demonstrated by trimming the aircraft at level flight, then putting aft stick for approximately 2 to 3 seconds. Bleeding off some air speed and then returning the stick to the neutral trimmed position. So the resulting response is usually oscillatory with significant variation in pitch attitude and air speed, while angle of attack remains relatively constant. In this, if you see here, very angle of attack is very minimal changes are there. Negative means it is a negligible change in alpha in this phugoid case. Very less. But u variation in the one direction only. It is not crossing. It is not a oscillatory. Okay, but it is in the one direction, but pitching will be in the both the direction. So the phugoid has been described as an up and down roller coaster oscillation. So if you see the aircraft is here, it will move like this, like this, like this, like this. Okay, so it is called the roller coaster. So it is either in this altitude will increase, then velocity will decrease. So here kinetic energy and potential energy conversion of these two energy will take place in this motion. So it is continue now. The characteristic phugoid mode. The aircraft then begins to lose altitude and airspeed increases while the pitch angle decreases. This is followed by the aircraft pulling up gradually and returning to the climb portion of the phugoid oscillation. The period for the phugoid is typically quite long. It is 30 to 120 seconds, but for the short period it is 5 seconds only. So that is it is taking a lot of time to stabilize. Notice that the response is also second order for the phugoid and that angle of attack remains relatively constant. In this, the frequency of the oscillation for the phugoid is much lower than observed for the short period mode. So in this, the frequency will be very less, but time it is taking more. So that is the case for the this phugoid mode, and this I have taken these references from the Robert C. Nelson Aircraft Stability and Control. And in the next class, I am going to further discuss about the other modes with the proper explanation for each different types of dynamic modes and try to explain all these mathematical equations and its application for different dynamic modes. Thank you very much for joining this class. Hope you have understood this well. So in this, we try to learn something and hope you all will understand clearly. Thank you very much for joining this class.
Like, share and subscribe. hit the bell icon for more updates.